Thank you very much, Tim. It's a great pleasure to be here. This is the first time to be in Mainz, and also I see many chemists more than ever I see in my life in this workshop, because I always go to engineering or physics community workshop and conferences. All right, so I'll try to give you some example or overview as electrical and computer engineers, how we can make some useful devices. Of course, it's very early to predict some real useful devices using these new materials. Once we have a new material, until we really commercialize, it typically takes 20 to 30 years, which also happened for silicon, also gallium arsenide, and so on. But let's try to see what we can do. So this is outline. So I'm going to give some overview, my view about nanoelectronics, nano-optoelectronics. Then I'm going to show some of the application using graphene, magnetic sensors, and terahertz devices, which I believe is most promising using graphene than any other electronic application. Then I'm going to show some of the research activities in my group using spin-orbital memory, using various materials like lanthanum aluminum oxide and strontium titanium oxide. This is perovskite 2-dimensional electron gas materials, and we are trying to utilize this one for spin orbital switching. And also the other interesting material is topological insulators. And topological insulators can be also utilized as spin photodetectors, because you have a spin momentum locking properties, which is very unique. And finally, I'm going to show our very recent data about spin lifetime in Weyl materials. Right? So if you look at three possible quantities we can utilize for devices. Number one is electronics, which really govern the modern electronics industry to make transistors or some memories. So if you look at transistor, electron has a very small wavelength, so you can condense in a very small form factor. In terms of flash memory, we can trap electron in a very small sort of regime. So once we trap this electron in this floating gate, we can maintain this electron for a long enough time, so we can make a useful memory. So this is the very unique property of electrons. But on the other hand, if you look at photon, this is used as communication, especially this fiber communication, because you can transmit information for a long distance. If you try to do that with other particles, it's not very easy because it's a boson. And the other problem is a lot of people try to make an integrated circuit with electronics and photonics, but it's not very easy because intrinsically you have this wavelength difference because of diffraction limit. Typical visible light or whatever, you have hundreds of nanometer feature size. On the other hand, modern electronics, people make 14 nanometer node size in Intel, for example, Samsung right now. So intrinsically, these two guys cannot be come into in the same picture. Nowadays, we are trying to utilize now this spin, which is basically the quantum information in electron. And in this case, information can be stored in magnetic materials for a long time. So once you have a magnet and you switch, 10 years, 20 years, we can maintain the information. However, if you try to send spin information in a non-magnetic material like copper, aluminum, or even graphene, it's very difficult to send this spin information over a long distance like micron. These days people report hundreds of micrometer, but if you look at real chip dimension, it's 1 cm by 1 centimeter by 1 centimeter. So if you want to send information for a long distance, at one of the edge of the chip to the other edge of the chip, it's not possible, basically. So in that sense, we have to think about what we can do with using these different types of particles. So if you look at the history of electronics now, it started the vacuum tube, early 90s, and then evolved with bipolar transistor. Then now MOS is basically governing whole electronic industry. And interestingly, every 40 years, we had a new sort of technology. We really revolutionized this electronic industry. And it's about time to have another new technology come into the picture. And what will be that, the next big show can be Spintronics, which we are here. And some people think it's a bio-related stuff, or like a holographic, or 3-dimensional display, and so on and so on. So we do not know, but it is quite clear, Spintronics can play a very important role. If you look at the other emerging electronics, we can divide in terms of area versus performance. For example, if you look at CPU, it's very tiny, 1 centimeter by 1 centimeter, and it requires very high performance. For example, modern CPU has about 2.3 billion transistors. If one transistor fails, so does the IC. So it requires very, rigorous treatment in terms of device fabrication. On the other hand, if you look at solar cell, for example, you need to make like a few meter by a few meter easily. We have to cover a whole loop, so it requires large size. However, if you look at the performance, it's not as rigorous as CPU. So if you have some defect in some of the the solar panels, still we can manage. So for this kind of application, we can now utilize this self-assembly technique for metal contacts or some of the junctions, even for the active area and so on. So a lot of people are trying to utilize, for example, recently perovskite solar cell. It's basically a chemical process. No problem. But if you look at microscopic picture, you have a lot of variation, I'm pretty sure. But that is suitable for this large area, low performance application. But in terms of now CPU, there's no way you can make CPU other than silicon at this moment. So we had the excitement of this graphene application. We can make all kind of electronics, logic circuit, and so on. However, by at this moment, it's kind of into a consensus that it will be very difficult to make any real electronic application using graphene. Right. Well, the other one is emerging technologies, this flexible electronics. So a lot of people are working toward in that direction. So we can wear some of the Google Watch and maybe some wearable computer in the future, and so on. So as I just mentioned, the modern CPU has like billions of transistors, and just one IC fails, and so does the whole IC. And the biggest issue in the industry is this uniformity issue. In a laboratory, we demonstrate just one device or a couple of devices in a very small form, and then we write a big paper. Sometimes we release a news media and so on. But in terms of real application, we have to make 300 millimeter wafer, very uniform, and we have to produce this wafer every other second. So throughput is also very important. And this is one of the difficult questions which graphene and other 2D materials cannot really answer. So if you look at the scaling of transistor, this is mostly lateral scaling. It's not really 3-dimensional, it's a 2-dimensional scaling. Now we are about here. The transistor is about 14 nanometer feature size, and soon we will reach this quantum limit. So what will be the next generation technology? Whether are we going to keep the scale down to atomic regime, or we're going to utilize some of the Nobel scheme using some other particle like a spin and so on. So that's one of the big questions. However, it is very clear now we have enough number of transistors. So if you talk to Intel people, no need to add any more transistors. Billion is enough. The biggest question is power, because it consumes so much energy because it flips so many times per given second, and interconnect, and each transistor it consumes a lot of charging and discharging energy loss. So this is one of the biggest issues we are facing right now, where spin electronics can play a very important role with low power consumption. Okay. On the other hand, now if you look at the vertical scaling, this now became a fashion these days. Successfully demonstrated for the first time by this graphite into graphene, and people got the idea, oh, so if everything you can make very thin, some novel feature happens. So if you look at recently, this MOS2 is the follower. is very famous solid lubricant. So whenever you have some issue, you go to the machine shop and you can buy this MOS2 lubricant and you spray. It really helps. But once you make a monolayer or bilayer, you can see very interesting direct band gap, optoelectronic application, high mobility, and so on. And the other one is this bismuth telluride and bismuth cellulite, the junction, which has been used for wine fridge for a long time. However, at that time, people use a very thick junction, like tens of micrometer. But once you make now very thin, 10 nanometer, for example, now there is some Dirac feature happens and so on and so on. So basically, we are rediscovering, all these nice, properties of materials by doing research. So this is the roadmap done by Novoslav and Philip in 2012, and they predicted, there will be very interesting application using graphene, starting from touch screen, then we can move to high frequency transistor and so on. In terms of optoelectronics, we can make photodetector, modulator, some isolator, even up to terahertz applications. And we are now 2016, so we are here, and are we really seeing some real application? It's quite questionable, but in my mind, some real value of graphene lies in sensors and optoelectronics, not electronics. So I'm going to show some of the data. So we always talk about silicon is a magic material. There is a slight misunderstanding about silicon. The beauty of silicon technology lies in silicon oxide, not really silicon, because silicon oxide is a magic material. It passivates the surface of silicon, so once you take it out, the pure silicon from a chamber, it immediately oxidizes 3 nanometer natural oxide, which is an excellent insulator, excellent barrier against impurity diffusion, and it has a high etching selectivity to silicon. So because of silicon oxide, silicon could make such a big progress. But if you look at, for example, gallium arsenide, there is no counterpart like this silicon oxide. So that's why gallium arsenide suffered, still suffering. It's very difficult to make like silicon. Of course, some niche market, high frequency transistors, we use gallium arsenide, some military application and so on. But it's a very small market. And silicon can be purified easily, defect-free, and all nice, electronics, mechanical, strong properties, and is widely abundant in nature and so on. So you can see why silicon is very important in modern electronics. And if you look at the dominant technology called the CMOS, complementary metal oxide semiconductor, the basic component is MOS structure, metal oxide semiconductor, meaning you have a metal gate, an oxide insulator, and semiconductor. So basically, this junction is the fundamental building block of modern electronics. And if you look at the operation principle, it's basically voltage controlled. Now, what does that mean? Once we apply the voltage here, basically we can modulate the accumulated charge in the channel. And once we apply different polarity of the voltage, we can deplete the channel. So basically, this is a switch, and we apply voltage on and off. So basically, this is a capacitive coupling device. So which consume very small energy compared to any other scheme. For example, if you look at spintronic devices, for example, this is a spin transport torque device. We apply large number of electrons to the device and transfer angular momentum from one to the other ferromagnetic layer. In this case, it's a current control device. So if you look at the basic feature, the voltage control device has the parallel connection capability. If you have a node and you have a multiple node basically, and if you apply the voltage in one of the nodes, all the nodes will be at the same equipotential. On the other hand, if you look at the current control device, basically it's serially connected devices. If you want to make a equal current, so you have many components basically. if you inject a certain current, you need to connect in series to make equal current. So that's why the voltage control device has a parallel connection capability. On the other hand, the current control device has a serial connection capability. So that really intrinsically limit how many components we can connect in parallel. Of course, we don't need to really stick to this operation scheme forever. We can devise some kind of a spin stuff without oxide, and probably we need a completely different approach if you want to make logic device out of spintronics, probably. But my opinion is we shouldn't really try to utilize same principle for spintronics. And if you look at in terms of spintronics fabrication, silicon fabrication, a lot of metals and this group 1 and group 3, 4, 5 regarded as bad materials basically, which must be removed during the silicon active region fabrication. For example, this is shallow acceptors and this shallow donors and so on. So a lot of gathering process is required to remove this kind of stuff. But nowadays we try to use these types of new materials with silicon process there, so that is quite challenging. But we don't need to really discourage because this is only restricted before the deposition of the gate. So that we call this the front gate. There's a back-end process. So once we deposit the gate, so that became now back-end process, then we don't need to worry about too much. So we can now deposit some other materials. Okay. In terms of optoelectronics, because the silicon cannot emit light because it's an indirect bandgap material. So now there is new opportunity. Some other materials can play a role in optoelectronics. So those are very famous photonic materials which we are using in our daily life. For example, we use all kind of LED based on gallium nitride and so on, which awarded a Nobel Prize recently to Suji Nakamura and all. And if you look at fiber communication, we use a lot of indium phosphide based modulator and LED, laser diode and so on. Of course, gallium arsenide is another famous optoelectronics material. So if you look at all these components, it's mostly single or binary elements, as I mentioned a couple of days ago. And as Josh commented, solid-state chemistry are way ahead, and engineers and physicists are way behind. So that's the problem. So hopefully we can see some ternary or even quaternary component in the future. But right now in the industry, they always prefer to have single element or binary elements because it's very easy to have sort of in terms of repeatability, multiple wafers, and easy to control, and exactly same stoichiometry is very important. And if silicon still can work as a photodetectors, not as emitters, it's very, very cheap. It's a few dollars. So if you try to use topological insulator or Weyl semi-metals for some kind of this photo detection application, I think it's kind of nonsense. However, because we can have spin selectivity, I think there is opportunity to make some spin selective or spin dependent photo detectors using these fancy materials. So I'm going to show some of our data later on. So in terms of emerging memory technology, probably you heard about RLAM, which is resistive random access memory. Hewlett-Packard is one of the leading company for this technology, and the flash is obviously the dominant technology right now, and MRAM is some rising technology right now. RLAM rely on stochastic breakdown. So we apply current and we form some kind of channels which coming maybe from some oxygen migration or so on, but the nature is stochastic. So if you make a very, very small junction, For example, in a given size, you want to make a very high density memory, 1 billion cells. Naturally, you have distribution, very wide distribution from junction to junction. So it's not very easy to control the uniformity. Basically, in a company, you need to satisfy like 3 sigma, 5 sigma distribution. It's very challenging. Flash memory relying on tunneling process to read, write especially. So it has endurance issue. Typically, 1 million cycles is its lifetime. So this memory cannot be used as the main memory of our computer. It's always side memory. On the other hand, the MRAM use intrinsic material property, so it's more deterministic. And recently, this spin transport torque was invented, which gives full selectivity. Also, we can make a very small cell size. So naturally, I believe this is the this will be the dominant technology in the near future. So in Spintronics community, not only this magnetic memory, we want to replace everything in CMOS. We have this transistor, which can be replaced by spin transistor in the future. So there is a bunch of people working on spin transistors in our community. In terms of interconnect, to connect one transistor with the other transistor, there are 20 to 30 layers of interconnection lines in modern semiconductor chip right now. And as you can see, this global connection has a very thick wire. Meaning, if you want to charge and discharge this thick copper or aluminum wire, we have to inject a lot of electrons. And you want to turn off, then you have to discharge these electrons. That's why it consumes so much energy. And the modern chip became like a nuclear reactor soon. No, it's a half and half. Transistor also, because you turn on and off billion cycles. When you talk about 2 gigahertz, CPU, meaning 10 to 9 times operation per second. So you can think about this guy charge for the channel and discharge. So you inject electrons, drag electrons back and forth, 10 to 9 cycles per second. So think about this. So a lot of energy consumed. So in the future, whether we can really change this interconnect with the spin waves, which we don't need to physically move any particle in spin waves, because the magnetic information can be transferred with basically phase. Locally, we change the magnetization direction, and we can move this information. So those are some of the other approaches. So basically, we are dreaming about this all-spin electronics in the future. I'm not very sure when we can do this. This can be our holy grail, but I'm pretty sure this MTJ, magnetic tunnel junction-based memory, will be in the market in the near future. Okay. So if you look at the horizon of the field of spintronics, people try to inject very high spin polarized electrons. That is spin injection part using copper ion and MgO, basically the combination invented by Stuart Barkin. And a lot of people use also half metals because in principle half metal should give us 100% spin polarization. Now once we inject this spin injection information, we want to manipulate. And for this, we want to have long spin lifetime. That will be great for example, quantum computers. Like now, Microsoft is working on it, and Google is working on it, for example. And also, we would like to have the long spin diffusion length, because ideally, we want to move spin information from one location to the other location. So that is for information transfer. For this, people utilize band structure engineering. Interface is known to be a key factor for spintronics. Or people think about maybe low spin orbit coupling material like carbon nanotubes or graphene will be advantageous. So a lot of people are also working in that direction. Recently, also people try to use these superconductors or very small nanoparticles, which may increase the spin lifetime. And spin wave is another way to transfer information using spin. So those are some of the horizons. People are working on it. So once we manipulate it, finally we want to detect. Of course, we can use electrical or optical detection to look at the information. Okay. So if you look at now the very successful major application of spintronics is reading sensors in hard disk drives, and this is magnetic media. And ever since invented, IBM showed the first hard disk drive, we keep shrinking the bit size, and the related reading sensor should be also shrinked. The basic principle of this reading sensor is spin-dependent conductivity, which was proposed by Neil Mott in 1934. So once we look at this spin-dependent tunneling or diffusion process, basically we can make useful sensors and also memories. So this is the core principle of spintronics. So this is the most successful application. This shows a GMR sensor. Typically, the magnetic resistance of GMR is only 10% right now in industry, and TMR, tunneling magnetic resistance, which also utilized now in reading sensors. Most of your computer use now TMR sensors in consumer electronics. It's about 50%, so not very big actually in terms of sensing, selectivity. However, this is a, we talk about only one junction basically. So once we make the GMR, TMR, wafer, we cleave, and then basically we, ship only one component for each hard disk drive. But now, when we talk about MRAM, magnetic random access memory, we have to build a million, billion cells in a certain size, and we have to have a uniformity of the device, properties. So making a high density array is a different story, compared to a sensing application, which is way difficult to make. So this is one of the major, problem right now industry is facing. For example, all the major companies are working on MRAM, like Toshiba, Samsung, Sony, Intel is working on it. Okay, so in terms of these magnetic sensors, not only for hard disk drives, actually in daily life you are using this magnetic sensor every day. You have a cell phone, open and close. How do they know you open or close? That is a magnetic sensor. Computer say, fridge. So most of the door, or you open and close, you have a magnetic sensor. So we always want to have a very, very cheap and very reliable, magnetic sensor. And in each car, there are more than 30, 40 magnetic sensors. And all the blue one is actually connected to some magnetic component in each car. So we try to make some useful sensors using graphene because naturally graphene is the thinnest material in the world. So if you ever shrink the bit size in hard disk drive, I thought it would be very useful to make a graphene-based sensors, so you can make a very narrow sensor. So this is one of our key data using multi-layer graphene. We achieved a very high magnetic resistance at 9 Tesla, about 500%. So if you look at the MR ratio I just introduced, GMR is only 10%, TMR is 50%, and this one is at least 10 times larger using very simple graphene. But the main problem is, for most of the sensing application, you have to have a good sensitivity at low magnetic field, because in most of application you will never get a few Tesla. For example, door, small magnet will not give us a few Tesla. Of course, there is certain application you can think about. For example, some industry or high magnetic fields facility, you need a very linear magnetic field up to some 45 Tesla and so on. But that is a very small niche market. And most of application, you have to have a very sharp sensitivity at a very small magnetic field. That's why GMR, TMR is very useful. And of course, this linear magnetic resistance is very interesting. As Maz introduced in the beginning of this workshop, I summarized all the systems showing linear MR, starting from indium arsenide, some silver telluride, multi-layer graphene, and even topological insulator shows linear MR. And recently, Mars demonstrated this the WTE2, while material shows linear MR response. Still, it's not very clear. People argue, there is a classical model and quantum model to explain those. So I'm gonna, shortly go over those. So the classical model starts from inhomogeneity. Basically, you have a P, N types of puddles, electron and hole puddles, which form random register networks. And because of the local mobility fluctuation, people explain it can lead to a linear MR response. And you can refer this to big papers. Okay, what is quantum model? And this is typical crystals, but once you have also inhomogeneity, now the tail can be formed, and because of linear energy dispersion, we can have linear magnetic resistance, which is temperature independent. Maybe you can refer to this paper for this quantum model. If you ask some more details, actually I don't know much about this. So recently we discussed with Antonio Castronito in our university, who is a great theorist. So we show our data, all kind of graphene data. Sometimes we have this parabolic MR with as function of magnetic field. Sometimes we have quite linear MR, something like very straight line. Sometimes we have different curvature like this, and so on. So then he sort of figured out, why do we just think about very simple two-channel model? So let's just assume in your device, basically we have two channel, one channel and second channel. Then depending on magnetic field, those two channels respond differently. Then you can have very different response. So he made this very simple model, and then turned out, once we have a large mobility difference between these two channels, basically the MR can be indefinite. It can be very large. So that was the motivation. So we try to make a device on top of boron nitride because it's well known, once you have boron nitride substrate, you can have very high mobility next to boron nitride. But once you have a multi-layer of graphene, away from boron nitride layer, the mobility will be quite small. So we have boron nitride and multi-layer of graphene, basically. So this guy will give a high mobility, and this guy will give us low mobility. So this is the basic idea. So then we can sort of model it. This is channel 1, and this is like a channel 2, roughly. So this is our key data. Once we realize this high mobility is predicted by a very simple theory, you can have very high sensitivity at low magnetic field regime. And indeed, that's what we can realize. You can see now we have very high sensitivity at low magnetic field regime, which gives at least several order of magnitude change in terms of magnetic resistance. And once we measure non-local, even we can measure up to 90,000% of non-local magnetic resistance, and which involves some of the thermal effect, actually. I'm not going to go to too much details, and we are very excited about this very simple opportunity, and our device works even up to 400K, which is very practical temperature for real applications. So we are actually discussing with some company for licensing this technology right now. Okay, so the other opportunity in terms of graphene technology is, I think, the terahertz application. And terahertz is being used for different applications like some weapon detection, some medical applications, semiconductor diagnostics, and so on. And one of the major applications is in the airport. So sometimes you need to go through this machine. It's basically a giant terahertz machine to detect some of the weapons and so on. So our aim is to make a small detector, something like this. This is basically a metal detector, but can we make a terahertz detector in this size? So this is our aim. And for this, we need a terahertz phase shifter, terahertz modulator, terahertz generator in a very small form factor. That's what we need. If you look at the modern terahertz phase shifter, for example, it uses a bulky magnet, which is about 200 to 300 kilograms, very giant. That's why the machine should be in this size. The other one is either we have to use this very high voltage in this fashion, because terahertz beam is in nature, the wavelength is like a millimeter, basically, hundreds of micrometer. So the device, contact distance should be separated at least that much. So when you shine terahertz beam like this, then once you apply the electric field, we can modulate the phase. But because of the large separation, we have to apply very large voltage. So this is the problem in modern terahertz phase shifter. But we found graphene has very low absorption in terahertz regime compared to any other transparent electrode material. Like ITO absorbs greatly in terahertz regime. However, graphene absorbs very little compared to any other material. So now what we can do is we can just put graphene top and bottom and then shine terahertz perpendicular to the layer. And in the middle we put LCD, liquid crystal basically, which you use for your monitor. And liquid crystal has the feature, once you apply the voltage, we can basically align this crystal in one direction to the other, and depending on whether it's aligned or not, the light propagation velocity will slightly change, so we can make a phase shifter. So we can nicely demonstrate this phase shifter as a function of the bias voltage, and you can see our device works at 5 volt level compared to 200 volt in conventional application, and it's very nice. So then we move to terahertz modulation. So it's a pretty much same device structure. It's top and bottom graphene layer, and in the middle now we replace liquid crystal with ionic liquid. Ionic liquid is known to have a very high epsilon R. So basically you can attract a lot of charge carriers at the interface. So once we do that, terahertz basically works as a intraband transition. So once you have a lot of carrier accumulation in graphene, we can modulate the Fermi level, and depending on the Fermi level, the optical conductivity change, and we can change also optical absorption. So if you look at the transmission of this device, it changes greatly with a very small voltage. So we can also make a double deck device, and we can even make 99% modulation, which is the largest ever reported. Right. So recently now we try to combine this terahertz technology with spintronics. So we, some of the group members grow these magnetic materials every day. So I asked him, why don't you just plug into our terahertz machine and see what happens? And we just put into the machine, and then we see there is a terahertz emission from these magnetic materials. So this is known as the working principle is inverse spinor effect. I'm not going to go too much detail. Basically, we shine femtosecond laser beam, and there is a spin-dependent diffusion of thermal current, and that thermal current, due to inverse spinor effect, there is a spin current at this interface, and that oscillation of spin-dependent current will emit a terahertz oscillation. So because of this is based on the inverse spinor effect, once we change this heavy metal next to copper, basically the phase change, which means if we have a platinum is known to have a positive spinor material, so we have positive signal. And if you look at, for example, tantalum is a negative because the spinor is negative. And this is tungsten, you can see negative, and ruthenium is positive, and so on. So this is another way to characterize the spintronics information at the interface. And we compared with the conventional zinc telluride terahertz emitter. So this is the most widely used terahertz emitter and terahertz detector. And our device works in a very similar way. So if you look at the intensity, it's almost same. at the peak value, and ours is somehow more uniform. But if you look at the thickness, this is 500 micrometer versus our device is only 10 nanometer, and our device can be fabricated by sputtering, very, very cheap. So we think there is some big opportunity in this terahertz generation. Okay, so this is for graphene. So I'm gonna switch gear to logic application. If you look at very bad transistor, which is the TFT panel, is a very dirty transistor. It's grown on a amorphous device or even glass and so on. So if you look at the on-off ratio, it's just about 100. Okay, when you turn on and turn off and just measure the current ratio, is over only 100. Conventional logic device requires this on-off ratio more than 1,000. Ideally, it should be million about for great transistor operation. But if you look at our spintronic device, like in this copper ion and MGO system, the on-off ratio is less than 10. Okay, and when we talk about TMR 100%, the on-off ratio is basically 1. So it is one order or even 2-3 orders smaller than the conventional logic devices. Some people try to use half metals because half metal is predicted to be 100% spin polarization at the Fermi level, but it mostly works only at low temperature. So if you work at room temperature, we never see a great performance. So this is sort of the showstopper for logic application using spintronics. So of course, in daily life, we use this mechanical switch, which is almost perfect, on-off. It gives a ratio because you physically contact and remove the contact. If you look at optical devices, for example, optical filter, the on-off ratio is also almost infinite. For example, we have a linear filter in this vertical direction. Once you rotate and then shine linearly polarized light, basically we will see nothing, which means our on-off ratio is almost infinite. It's also true for microwave devices, which we use for the local baseband antenna station. Use a lot of microwave device. For example, this is a 3-pole circulator. The simple device, the signal is coming in, and depending on the magnetic field, we can move this information into only one direction, either this direction or this direction, something like this. So it has also very perfect selectivity in terms of energy flow. Is there any similar component in spintronics? Unfortunately, not really, but we can think about this spin waves is kind of wave propagation, which we can use for information transfer. So this is a single electron spin case. We apply magnetic field. We have this precession, Raman precession. In case of a 1D chain, we can move some of the information from one to the other because in a given location we just change its magnetization. Okay, so there is no physical motion of any particle, but once you have this continuous change of local magnetization, we can basically transfer information. And this is the uniform precession. Typically, we call this ferromagnetic resonance. So all the magnetic moments moves in a same phase. But if you locally magnetize, and manipulate the magnetization direction, we can also move information. So this is kind of plane waves from one to the other. So basically, spin waves can work as a some of the information carrier in spintronics. So we are trying to manipulate these spin waves and achieve a very large on-off ratio. So this is our device. We build a device with tantalum and the permalloy, which is very typical 3D ferromagnet in industry. Then we put antenna here. This is coplanar antenna, and then we can excite one of the antenna with the pulse generator and measure in the other antenna using oscilloscope. So depending on the thickness of underlying tantalum layer, we see a big difference. This is a typical device. If you look at, you can just think about the blue and the red constitute, opposite K vector, which is equivalent to opposite magnetic field. So one wave propagating, right direction, or the other wave propagating left direction has sort of, twice of the difference in terms of amplitude. So on-off ratio is very small, basically. It's only 1 or 2, depending on how you calculate. But as you increase the tantalum thickness, if you look at, for example, this case, we can see the blue one is still quite, strong. But if you look at the red one, which is propagating in a certain direction, is almost 0. So meaning the on-off ratio can be up to 60. So the underlying principle is the energy loss due to spin pumping. So once we have a tantalum layer underneath, and depending on the propagation direction, we can absorb this energy of the spin waves into this tantalum, because tantalum is a heavy metal layer. And I think this one applies for the same material like Weyl materials or even TI, because you have strong spin-orbit coupling in these materials, and possibly we can manipulate this absorption by certain scheme. Then probably we can even achieve larger on-off ratio. Okay, so let me move to another topic. Nowadays, people try to use this spin-Hall effect to manipulate the magnetization for memory application. So we know the Hall effect. Once you apply the magnetic field, carriers are deflected, one direction. Then we can measure transverse voltage. What is spin-Hall effect? In case of spin-Hall effect, there is no need to apply external magnetic field. Once we have the spin polarized carrier in the channel, because of high spin-orbit coupling, we will have accumulation of one kind of spin at one interface and the other spin on the other interface. So recently, Myron et al. Demonstrated in platinum, once we apply charge current, and because of this spin accumulation, we can switch one of these ferromagnetic layer from one direction to the other. And this is called spin-orbit torques, to distinguish from conventional spin transfer torque, in which we need two ferromagnetic layer in spin transfer torque. But in this case, we do not need another ferromagnetic layer, which is typically used as a polarizer. But here you have only one magnetic layer and just heavy metal. And also we apply current along the in-plane direction. So there is some controversy about what is the underlying physics, whether it's coming from Rashba effect or it's coming from spin-Hall effect from the bulk of heavy metal. A lot of papers are coming every day. But what is clear is this effect is so strong, so we can utilize for real memory application. What it means, once we fabricate magnetic tunnel junction with this high spin-orbit coupling materials, utilizing this spin accumulation, we can switch one of the magnetic layer, and the other one will be just a fixed layer. Then we can realize memory. In conventional spin transfer torque device, we have to apply current into the cell, and in order to switch, we have to apply a lot of electrons. Okay, so that damage the MGO, and also gives some instability, all kind of issues in terms of device operation, and also reliability was a big issue. But SOT solves all this kind of problem because we apply current along the metal line, and the metal line is much stable than oxide or any other semiconductors. So what is spin-Hall angle? Just give a very brief introduction. Basically, we inject charge current, and the heavy metal has a high spin-orbit coupling, so there is spin accumulation that will diffuse into ferromagnet, give rising a torque. So it's defined by basically spin conductivity divided by charge conductivity, and there is some geometric enhancement factor, which is the device length over thickness. So the spin current can be very large because typically the device length is 1 order or 2 order larger than device thickness, and spinor angle is typically 0.1 up to maybe 2, depending on materials. And this material parameter is a spin-orbit coupling phenomena. So basically, this spinor angle is proportional to g to the 4th. So if you look at copper, it's very small spinor angle, and tantalum or tungsten gives a very large values. Is it always positive? Not really. If you look at one of the columns or row or periodic table, depending on how many d electrons are filled. For example, tantalum tungsten is negative, and platinum gold is positive. And luckily, some CMOS compatible material shows a large spinor angle, like for example tungsten or some tantalum, and also most of these Weyl Dirac semi-metals has a very large spin-orbit coupling. So this is another opportunity we can look into. Okay. It's really a constant value for a given material. There is also a very controversial report. Even in platinum, some group report more than 0.1. Some group reported is 0.005. So we try to plot all the data using different technique, and it forms a very nice inverse relationship between spin diffusion length and spinor angle. So you can naively think about once you have more scattering. So spin diffusion length is very short, spinor angle is larger. If it diffuse long distance, basically spinor angle is smaller. So it's basically scattering event. And also it has a linear relationship with the conductivity of materials. Which means when we can engineer also for a given material. So as grown, we have certain value of platinum spinor angle, but once you anneal at different temperature, basically you can manipulate grain size. Once you have a larger grain size, you will have a longer mean prepass, which means spinor angle will go down. So this is a very simple manifestation of this spinor angle for a given material. Then recently we got a very puzzling data. We tried to oxidize our the films. We have a platinum copper ion boron, and then we have capping layer. And depending on the capping layer thickness, we can change the amount of oxygen incorporation into the device. Without proper capping, we see is anti-clockwise switching, which means our spinor angle is negative. Okay? But once we have a proper capping, we see it has clockwise switching. It means it has a positive spinor angle, which is a very conventional report. Many groups reported this value. So we are puzzled by this weird data, and it turned out there is competition between the Lashiba effect and spinor effect. So we believe this is dominated by the surface Lashiba effect. On the other hand, this one is dominated by bulk spin-Hall effect. So this one suggests the role of interface or some oxygen bonding in the device. I'm going to go to too much detail. Just want to give a brief overview what's going on in the field. So this is a very simple comparison of spin transport torque phenomena into the cell. The current is going directly to the cell, and this is a spin orbit torque switching current. So basically, in industry, for application, we want to reduce this switching current as small as possible. So what is the best way? If you look at the formula, the best way is to enhance this spinor angle. So if we have a larger value of this, basically we can reduce the switching current. So this is basically holy grail in this field. People trying to achieve a very large spinor angle from various materials. So different groups use a different approach, like iron platinum, copper bismuth, or beta-based tungsten. And team just reported, oxidization of this tungsten can also give a very large value and so on. And this is our group's report. We try to introduce a multi-layer concept. So once you have multi-layer, you can have even very large spinor angle. So still the field is evolving. And some other new addition into this picture is this two-dimensional electron gas, which we introduced recently. So once you have this LAOSTO, there is a two-dimensional electron gas formation. And depending on oxygen partial pressure, you can make this interface anything, superconducting, ferromagnetic, antiferromagnetic. You just name it, you can make it, depending on oxygen partial pressure. So it's another magic materials for science. So we try to look at the property. So first, we made a ferromagnetic interface by adjusting this oxygen partial pressure. So once we have a magnetic interface, we can measure AMR. So we rotate magnetic field in plane, and we can see nice typical oscillation of AMR. Then we apply DC current into the channel, and because of very strong Rashba effect in these materials, depending on current direction, the Rashba field exists into this orthogonal direction to the current direction. So depending on the current direction, we can see a very asymmetric response of this AMR. So once you look at this, at 0 DC current, we see very symmetric response, but now it's distorted in this form. So depending on the amount of injected DC current, we can extract how much Rashba field we have, and we can get up to 2.5 Tesla with very small current. So once you convert into some reasonable current density, people want to typically compare 10 to 6 amp per square centimeter. We have about 36 Tesla effective magnetic field. It's crazy. But once you convert this number into a typical Rashba parameter, it gives a very reasonable number. And it's not really surprising. People knew the existence of Rashba field in this material system, but nobody ever looked at as a function of injected DC current, which we nowadays call as a spin-orbit talk. We kind of revive this phenomena. So some people think this is nothing new, but some people think it's entirely new concept. Just let you decide. So recently we measured also some anomalous Hall. I think it's too much science, so I'll just keep those to the main topic of this workshop. So topological insulator is very exciting because there is opportunity of this spin momentum locking properties, which may give us a giant spinor angle. So that really motivated us to look at. First, we have to prove during the microfabrication, we need to do etching, deposition, all kind of process, whether this surface state survive after this process. So we first evaluate all this process, especially etching is one of, I think, headache we need to think about. So we did ion argon milling, which is typical dry etching for our device fabrication, and we found the device resistance. This is before the milling. This is gate voltage versus resistance curve, typical Dirac curves. And once you do the milling, we can see the resistance drops, meaning there is some defect or disorder incorporation, give us slightly smaller resistance. Oh, this is not very good. Then we try to look at magnetic resistance. Typically, it gives a linear response depending on temperature. Low temperature gives a linear response. High temperature gives a parabolic. So it's quite interesting. Maybe this is direct proof of linear band versus parabolic semiconductor band. We don't know. But the interesting thing is once we do this argon milling, this linear MR became there is contribution of negative MR. So there is this kind of curves happening, which from some various measurement we attribute this is originated from disorder due to argon ion milling. But I saw some similar behavior a couple of days before. Some people showed from your wire materials. Once you do the MR measurement, sometimes you see this negative contribution. Maybe it could be due to disorder. So then we try to look at the weak anti-localization, because this is a typical measurement to look at quantum basically coherence. And we found before the milling and after the milling, this weak localization parameter is fairly reasonably constant, minus 0.5, doesn't change much. And once you look at the phase coherent length, it's almost same. So we conclude, even though the bulk property may change because of the disorder, but however, if you look at the surface property, it looks robust against this external damage. So we are very happy about this result, and we moved to real device fabrication to measure spin or angle. So our choice of method was spin pumping. So basically we change this magnetization and inject spin current, and we look at inverse spinor measurement and detect the voltage. So I'll just go directly to the data. At room temperature, we see the spinor angle is only 1%. In terms of ratio, it's a 0.01, very small, much smaller than that of platinum or that of tantalum. So very disappointed. Then we cool down. Maybe this will happen only at low temperature, but once we cool down, we see the spinor angle only move up to 2%, meaning 0.02, only 2 times improvement. Not very good, something wrong. So then at that time, when we reported this, we submitted to some high impact journal, but referee commented, oh, your data is very discouraging. There is no evidence of spin momentum locking. What are you doing? And similar time, we saw very encouraging report by Cornell. They claim spinor angle is 2. So in terms of percentage, 200%. UCLA reported spinor angle is 140. So once you convert to percentage, you have to add 2 more zeros. So if you look at from here to here, 2 order difference. From our data to here, another 2 order difference. So from our data up to this, 4 order difference. What's going on? So we try to use exactly same method like a Cornell. Okay, guys, let's use the same method and see what happens. Right, so this is our data. At room temperature, we see the spinor angle is 0.04. Okay, not much, 4%, 5%. But once we cool down, we see huge enhancement below 50 Kelvin. And then it shoot up to 0.45, more than 10 times improvement at low temperature. And this one has a very direct correlation with temperature response of conductivity of this material, bismuth selenide. If you just measure bismuth selenide, it's a very bad semiconductor. It's metallic basically. So once you cool down, you see a plateau below 30 Kelvin. And people think this is a signature of surface state. Okay? And at this temperature regime, we see huge enhancement of our spinor angle. So we believe this is a direct evidence of a spinor angle. Of course, we did many other analysis why surface state is responsible for this observation. But I'm not going to go to the details to this. And once we do a little bit more analysis, into 3-band model, like there is surface state and the Lashiba 2-dimensional gas, also bulk contribution. Then we try to look at the current shunting model and how much current really go to the surface state. Then we extract what is the effective spinor angle, and then we turned out it's about 2 or 1.6 depending on how we analyze. And this number is amazingly similar to what Cornell reported at room temperature. Okay, but our data is at low temperature. So still, we don't know, what's going on. Maybe it's coming from the quality of materials, or maybe it's coming from something else, how to make the devices. So we keep looking into that direction. So this basically summarizes all the report from topological insulator spinor angle. This Cornell data, this is our data, and UCLA data. And if you look at the spin pumping, this is our data. And at similar time, also Tohoku reported using spin pumping, their spinor angle is 0.01, exactly same number. This is Minnesota, recently came. My postdoc moved to Minnesota and doing the exactly same thing what we are doing. And they measured the spinor angle is from 0.01. So if you look at spin pumping, it's kind of, they agree, 0.01. But once you look at STFMR, it's like a 2. But please note this is low temperature data and this is room temperature data. Using spin orbital switching method, UCLA show enormously large. Of course, this is a slightly different material. They have a chromium doping in TI, so it's a different material system. But I just want to show a whole horizon of this field from very small number up to 4 order larger magnitude. So I think it's a very interesting research area and potentially revolutionize magnetization switching. One thing to note is we have to be very careful because when we measure the device performance, we are not only measuring topological insulator surface state, but also some Lashiba splitting bands. And if you look at the supported spin momentum locking, actually it's the opposite. For example, if you look at this guy, it's up, but your next Lashiba band is actually down. Okay? So if you just make a device and apply current, basically you move your Fermi arc to one direction, and basically we are measuring average defect of all these bands, depending on our Fermi level. And typically our Fermi level is way beyond the Dirac point, typically like 300 millieV or 400 millieV. So we are here. Okay. So we don't know whether we are really measuring surface or is average defect, even probably some bulk contribution. So that's why I think Weyl material gives an opportunity, because bulk is so much conducting. Now we don't need to worry about, because bulk will be dominating. So once we know exactly the bulk property, maybe we can tell what will be the spin or angle from Weyl material. So we try to look at other methods, but I'm just skip those. Using photocurrent imaging, we can really look at the spin accumulation. One side versus the other side, we can see different color, meaning one spin accumulated one edge, and the other spin accumulated. Then we can look at optical conductivity and deduce what is spin or angle. It's only 0.01, which is exactly the same as our spin pumping. Okay, and also we can think about, as I just mentioned in the beginning, the spin-dependent photocurrent is another application we can think about using topological insulator. Okay, so I just summarized all the spin or angle from various materials. This is metallic stuff, and the TI gives a relatively larger value of spin or angle up to 2, multi-layer. This is a UCLA topological insulator. This is our RAO-STO 2D heterostructure. So we don't know whether it's going to end or keep continuing. So finally, I'm going to just show 2 slides about this very interesting, very hot data we got last week. Because I had to have some wild data to show in this workshop, so I pushed my postdoc. Can you guys generate some data so I can show? So this is WTE2 material made by CBD method, made by different professors. It's a very large size. It's hundreds of micrometer up to millimeter, and it shows a good Raman data. And we used time-resolved curve measurement to look at the spin lifetime. And this is a typical data. You can see with the one circular polarization, we can see a decay of this curve signal, order of nanosecond. With opposite polarity, we can see exactly opposite, which means this is really spin phenomena. And once you do a subtraction, then we can now measure this curve rotation as a function of time. Then we can extract what is the time scale using this bi-exponential fitting. And the first decay time is basically the hot carrier dynamics. Sometimes people call demagnetization and so on. The second time scale is more related to real spin lifetime. And amazingly, this one gives 1.2 nanosecond decay. This is typical data from our topological insulator, bismuth selenide, using same method. Now you can see here is order of picosecond decay. So once you extract the spin lifetime, it's only 1.3 picosecond. So if you look at this versus this, 1,000 times difference. So we are very new to this field, and we try to understand. And my postdoc, proposed this concept of spin dynamics model using this conventional band structure reported by many others. This T2 or tau2 is related to interband electron hole recombination and also backscattering. But if you look at those 2 events, both are prohibited because of backscattering is prohibited because of time inversion symmetry, and tau r is also very difficult because the momentum space is separated. So I'm not going to go to the summary. As you can see, most of the data from other 2D materials, the spin lifetime has been measured at low temperature, and none of that really show extremely long spin lifetime at room temperature. And this guy is only materials. So amazing material. And then we applied the different magnetic field, and it's very robust, meaning probably very strong spin-orbit coupling stabilizer spin lifetime, which we don't. So some open question. We need, I think, some beyond band structure in Dirac-Weyl this field. I heard a lot of band structure calculation, ALPS, and so on. But as a device physicist, as an engineer, I want to see a useful device proposal from you guys. And what are the properties we can utilize? It's a spintronics, spin momentum locking. But if you have a Dirac band structure, you can always think about intraband optical transition, which is very useful for terahertz application. All right, for this, I want to acknowledge all my postdocs and students who really, did all this measurement every day, and also collaborators from various institutes who make, this work happen. Thank you very much.